So as is the co-authored paper, so as you see, we have 2 lead authors, Stacey's here, and 2 senior authors, Charlie's one here. It was a whole set of really excellent co-authors. This is what we call the whole collaboration. And like all massive collaborative good things in evolution biology, this was sponsored by NIST. I also thank David Baum, Matt Streisfield, and Ned Friedman for looking at previous drafts of this work. Okay. So you look at flowers, we see all this diversity. Right? And part of our work as evolutionary biologists is to go explain why is the world the way we see it. Right? Why are there so many flowers that have few stamen or bilateral symmetry and things like that? That's our mission. Well, it's been our mission for a while. And so some early work on this was done by Larry Stebbins in 1951. So he looked at various eight key characters used in plant classification, and he polarized them as ancestral and derived, and then looked at the distribution of these traits across plant families. Okay. And created this sort of hard to understand chart. Look at this. Right? So to unpack this a little bit, that first upper left-hand corner there, right, says 12 families have the presumed ancestral state for all traits. Okay. Down here, no families have the presumed derived trait for all 8 traits. And 36 have few stamens as a derived trait, few carpels, and 1 single carpel. Okay. So he looked at this and did some analyses and said, you know, plants are clumped. So these families are clumped in trait space. And his thinking was that these combinations of characters indicated natural selection. Right? So these aren't neutral traits. Selection is finding these ideal combinations and selecting for them again and again and again. Okay? And that was his story. And it's great, right? But it leaves a few things unresolved through our modern eyes. Right? So first, what's the mechanism? So it could be natural selection, selecting for these traits. Right? But now, of course, we're in the land of BISI, right? So it could also be differential diversification, a combination of the two. Right? There's some other processes as well. Which traits matter most? So we found that through these clumping, that's a good step. But does having petals versus not having petals matter? Or is it position of the ovule? Is that what matters for diversification? Okay. And is this pattern truly non-random? Right? So since life is this branching tree-like process, life is clumpy. Right? So we have to do independent contrasts and things like that. And so is this pattern truly random? Or is it just as a result of having a tree? So we set out as a working group to solve these questions. So how do you do that? So first, actually, understand I should look at life, plant life taken at random, right? So we could do, the key taxa, include umbrella, things like that. But for these analyses to run, one of their key assumptions is that you use sample taxa at random, with regard to taxonomy or traits or other things like that. So to do that, we did a 2-step sampling process. So first, we figured out from a list of a database of plant family size, how many species are in each family. And then from that, we figured out how much representation should be from each family in our final data set. And then we went to GenBank and picked that number of species from those families. Okay, so that way, if there were some family that was present in much of GenBank, we still don't overcorrect for that. We still don't have too many of those. Okay, so we do that very careful sampling. Then we take those species, chosen at random, and build a chronogram. Now, the goal of our study wasn't to build a new tree of plants. So instead, we did a very highly constrained tree with lots of date constraints from Susana Magallon. We used a new dating program for that. Okay. Then we had to score traits. And this led to a discussion about character states, right? So you have a whole bunch of people who understand plants really well. Talking about homology requires a lot of discussions. We had multiple meetings about this. It's really good to see people, and it's amazing for me to be with people who could say, oh yeah, that plant in Madagascar has an inferior ovary. Okay. And once we did that, we went out to the literature and identified for these plants what their traits were. Okay? And this could be hard because some of these are chosen at random from GenBank species. Right? So some are very common, easy to find, some weren't. So we went out and did this. Then we did the BISI thing, right? Which we'll get to in a minute. We evaluated monols for trait change and diversification. And we actually had to do some extensions to BISI and MUSI to be able to do this. And we call that extension FAMASI, or famously. Not really famous, but famous-y. If I want to know about, is this repeatable? Right? Is what we see expected, or does it just come about by chance? And so we wanted to replay the tape of life, and so the Gouldian sense, to examine reproducibility of this. So we developed a new stochastic simulation approach to do this. So first we took Stebbins' list of 8 characters, give it down to 6 characters. Corolla present, absent, perianth, separate, fused, radial symmetry, bilateral symmetry, many or few stamens, carpels unfused, carpels fused, and ovary superior and ovary inferior. And like Stebbins, we polarized it. So we said the ancestral flower has these combinations, these traits. And all our analyses in BISI and all our simulations started with this assumption of this being the ancestral state for flowers. So then we took these, rather than looking at that crazy table of Stebbins, we just categorize each possible combination of traits, right? So we could say this combination right here, right, has the ancestral corolla status, which is present, ancestral perianth status, ancestral radial symmetry, but it has fused stamens, fused carpels, and a superior ovary, right? So there's 64 of those possible combinations. And then we went to our evenly sampled set of plants, and look and see what the actual distribution of traits were. Okay, we got this. And so these bars show the actual frequencies in our data set. Right? So some combinations are much more common than other combinations in our data set. And this gray region shows a 99% confidence interval of if we just assume even frequency of these combinations at random, and then ordered them, what we expect for this histogram. And we expect some histograms to fall somewhere in here, and of course this is very highly skewed. So great, so plant life is very highly skewed for combinations. So Stebbins was right in that way. But we still don't know correctly for phylogeny. There could be some factor where orchids are very common to reverse, but it's not due to these traits. So we don't have to correct for that. One thing to note, a little bit of foreshadowing, is the root state here is still present at high frequency. Okay? So we'll come back to that. So here's Stebbins' idea, right? So we have these 2 traits, and we have natural selection driving us presumably one way. It's not the only way traits change, of course. So you could also have drift or mutational bias driving us one way or the other way. And Stebbins and we look at multiple traits, combinations of traits. So in the single trait, we're looking at 0, 0, and 1, 1, and all these combinations throughout. And now, of course, we know that what else can drive this pattern is speciation and extinction processes, too. So that include those parameters. Right? So, are these all the factors that can lead to contemporary distributions? No. We're missing some stuff. We're missing time and chance. Right? So if we happen to start in this state, and we come back 5 million years later, we can still be in this state. The equilibrium might be being mostly in this state. We haven't had enough time to get there. Okay? And chance can also play a role. Maybe we start here, and we could be going here and here. But if we replay the tape of life at the same rates, we would stay here a lot longer and eventually go this way. And so how predictable is what we see in nature? So that's things that apply. Okay. And also we want to, since we can't separate natural selection, drift, and mutation, we just group them as interspecific processes. Right? So we don't know which process is happening. So for 2 binary traits, this is feasible, right? Must see 2 so 8 transition rates, 4 birth rates, 4 death rates. Cool. If we want to do 3 binary traits, it gets a little harder. 4 binary traits, now it's getting chewy, right? And we want to do 6 binary traits. So we want to estimate 384 transition rates, 64 birth rates, 64 death rates. This is a very bad idea. So how do we solve this? So we care about these combinations, we can't estimate this full model. So our solution is focal areas. So imagine we had a hypothesis about just this particular trait combination. Just having corolla present, bilateral symmetry, and fused stamens. We say, you're special. You have a faster diversification rate, or lower diversification rate, or somehow unusual relative to other plants. Okay. This is how we do it BISI in general, right? If I said, I want to look at inbreeding versus outbreeding, I'd say, all I care about is inbreeding as a state. And I ignore whether you're woody, annual, or everything else. And so we can look at these and develop these combinations where we say, okay, do you have this combination or not? And then we can map this onto a network. Okay. So now we have that neural network. Now we have these focal combinations and everything else. And we can separate it and then just make a very simple model, right? Where we have one diversification rate for these that have that combination, one that doesn't, right? Distribution between these, distribution among these. So as a way of simplifying this very complex model to be feasible. And of course, we can try multiple different ways of doing focal areas. A single trait, like regular busy, 4 characters, pair of characters, etc. And for these models, we can actually simplify them too. We can simplify our transition model and our diversification model. So combining all these, we have 5 possible transition models, 6 diversification models, 3 of the 6 possible areas. So we have to look at 19,000 models. So we can do that, powerful cluster. This is likely using diversity tree, calculate AIC. We do that, and found we got 99% of the weight on just 10 models. So we had 19,000 models in the set. Most of life said it's these models. And these models said that these traits were often important, so correlate present, bilateral symmetry and statements few, are in many models, bilateral symmetry is in all models. They're important. We have lots of diversification parameters, but our transition models tend to be simple. And so we can do a model average result to show the overall transitions. And here we see circle area is the number of stacks in that state, and then we have these rates going into out of it. And color shows the net diversification rate. We see how this lump here is the fast diversification rate. So conclusions from this, bilateral symmetry is important for floral diversification, but so is having few stamens and having a corolla. All these relate to pollen placement, we think. And different diversification rate matters more than different transition. We haven't gotten to time and chance yet. So let me skip ahead a little bit. Here's our reconstruction of these traits. And so we do a forward time simulation, starting from this presumed ancestral state, and replay the tape of life multiple times, and see and compare to our actual distributions. Okay. And so we get, here's our fast trait, which evolves eventually. And so we find that this presumed fast diversifying trait takes median 71 million years to evolve, right? And so the fact that we have so many of the ancestral states still just shows that we're sort of decreasing that frequency through time. We haven't gotten to equilibrium yet, okay? Even despite 136 million years of evolution and 250,000 species. Okay. So conclusions: flowers aren't all diversifying fastest in the fastest combination because it took millions of years to actually get to there. And thus macroevolution could be limited by microevolutionary transitions. That's way of combining macroevolution and microevolution. So, other questions?